let's talk about Sturm-Liouville theorem. Brilliant. Farewell. All right. So, you're getting 2 lessons at the chalkboard today. I've got a new notebook. And it's already filling up with stuff. I think I've taken like 6 pages of notes this morning or more. But Sturm-Liouville, you don't need to be deep into physics to know where this thing shows up. That's what I really like about it. It's not at all what you might think. Your math anti-bias is showing up just for ODE. Well, I think that's kind of one of the cool things about this. So let's write out the whole thing. And I think that NC probably knows what this theory is. So maybe you can add a couple cool things about it that I'd leave out. But we're going to write the full differential form of Sturm-Liouville. Okay, the full differential form looks like this.
I am sure a doctor can check for that chat on your arm.
Not swole, small. So it's the derivative with respect to x of some function p of x dy dx plus qxy, which is equal to negative lambda. We're going to use w. I guess you can use r in some cases. A couple of the places I was looking at had w as r and r is, and then a couple other ones had r as w. So this is what we call the Sturm-Liouville equation, and solving this is the Sturm-Liouville Liouville. Whew, it's gonna be a rough one. Liouville theory, right? And this is a class of differential equation whose purpose is to find the value of lambda that give infinite values as solutions to the ODE. Now, there's a little bit more that we're going to have to unpack from that. You're going to see a couple of these things, but I think what's kind of crazy about the Sturm-Liouville theory.
For Princess Melko to join chat and troll you.
I'm sure she will. I'm sure she will. But I think what's pretty cool about Sturm-Liouville is that this is a second-order differential equation, and it's literally every second-order differential equation. Like, you can write every single second-order differential equation this way. Now, where does this stuff show up? Well, let me give you a hint. Everywhere. Like, this is everywhere in physics. So, all second-order differential equations can be written in this form. I think it's wild. Now, if y solves so we have y here, and y here, and if y satisfies some boundary conditions, then we call the y at those boundary conditions, or the y that does satisfy those boundary conditions, as that is a Sturm-Liouville problem. And what you'll find is, like, we'll have solutions to this such that we can let y be 0, right? We can let y be 0, but y equals 0 is a trivial solution. So we're not interested in that. And then we have some names for these things, and you're going to see why we name them once we start unpacking them a little more. But when y is equal or not equal to 0, then we call that an eigenfunction. With lambda being the eigenvalues. Kind of interesting. So where does this show up, right? We know that this shows up in physics. I've told you this shows up as literally every single second order differential equation. So what's a good, give me a second order differential equation. Come on, what do you got? Harmonic motion. Absolutely. I think so. Actually, it's not one that I have on here, but yeah, it's kind of the same. Actually, yeah, it would be harmonic motion, simple harmonic motion, right? We could write the wave equation. Actually, it's like the first example, so I don't know what I'm talking about. But yeah, the harmonic motion is a big one, so let's talk about that one first. How about an example of a one-dimensional wave equation, right? So a one-dimensional wave equation. So a 1D wave equation has some shape that looks like this, and this is a simple harmonic motion, right? Right. So we'll have some wave equation that looks like that. This also shows up as Poisson's equation, right? We can talk about Poisson's equation when we get into higher one dimension. We're gonna keep it one dimension for now. And if we were to do an example, we could solve there's lots of examples of this in Griffith's E&M book. Because one of the first things you do is you see Poisson's equation and Laplace's equation, and then you have to do Laplace's equation in one dimension, Laplace's equation in two dimensions, and you get all sorts of cool and interesting things. But another, so let's see how we can make this out of Sturm-Liouville, Liouville, excuse me. Well, we'll have to do the following. What if we take our function p of x, set that equal to 1, set w of x equal to 1, and set q of x equal to 0. So now let's go back up to here and see what we have here, right? If p of x is equal to 1, and then this just means this is the double, or this just applies to here, and we get the double derivative with respect to y. So we have, this is 1, so this will be absorbed into here, and we'll go d2y dx squared plus, well, q of x is 0, and then w of x is 1. So then we just get negative lambda y. So then that's basically y double prime is equal to minus lambda y. So we can find solutions of lambda, namely ones we already know, like lambda. I think this chair is in the way today. Like lambda equal to n squared pi squared over L squared, right? Now that gives us eigenvalues that solve our function, our y, or eigenfunction of sine n pi x over L. And if you were to do, and this is a pi x over L. Yeah, if you were to do one of these boundary problems in Griffiths, you would find out we would have to do like the Fourier series, and you would end up getting values like this for the 1D or higher dimensional waves. I think they usually do a lot of 2D stuff in Griffiths, if I remember right. Because you do a lot of separation of variables. But either way, this would be an example of one of the most famous things written as in the Sturm-Liouville equation stuff. So there's other ones that we can talk about as well. So we did that one. That was like kind of the most famous one, would be like the Poisson's equation, or it's also the heat equation. It's also simple harmonic motion. So you do it with things like the dynamical matrix of condensed matter. But there's other ones. How about this nice one? We're going to call it the parametric, just because it's parametric Bessel functions. Parametric Bessel functions. Oh, I wrote that so weird.
We are experiencing static.
Are you? All right, we're going to go with that, and we'll see what happens. Hopefully it doesn't come back or bother you guys too much. Just let me know if it's still going on, and we'll work on fixing it. Anyways, where were we? Oh, yeah, we're talking about parametric Bessel functions. We know the Bessel functions come into play in like pretty much all of quantum theory, right? We have to deal with Bessel functions. They're awful. One of the worst things that I have to solve.
Anubis knows there is a lot of room for the microphone.
On my nose. He's talking about my nose, guys.
Your nose hairs are causing static electricity.
All right, you two. So the Bessel functions, the parametric Bessel functions, let's write this out. Usually it takes the form that looks like this. X squared y double prime plus x y prime plus lambda squared x squared minus m squared y equals 0. And for the Sturm-Liouville form, or Liouville, it's P of x is equal to x. Q of x is equal to minus m squared plus, or divided by x. And W of x is equal to x. So those are the solutions. That's basically what we need to do to prove, or to find, I guess, define the eigenfunction and eigenvalues associated with the Bessel functions. Now, one thing to be noted about these is that P, Q, and W always have to be greater than 0. But you might say to yourself, Eric, there's a minus sign. So that just means that we have to talk about what solutions of M will be allowable, especially since it's squared. Actually, I don't know what that one is. Hold on, let me look at that one. Now I'm just looking at that. Now it looks a little odd to me. Because m squared can't change that unless it's complex. Oh, maybe that's the trick. Maybe you have to make m complex. Let's do one more, and this one was a new one for me that I have never seen before. But PhysicsOH had mentioned this in the past, and that is Chebyshev. I think others mentioned it as well, but I always remember him mentioning this about something about super, what is it called? All right, so Chebyshev, this one is very different. This one is for like someone like Doe who's interested in where like hypergeometric series show up, because this is the hypergeometric solution. I got a little ambitious with this. There we go. So the Chebyshev is like a list, or it's like one of the hypergeometric series that shows up when you're modeling like atoms and things like that. So this would be the differential form of it, and then of course you can make it Sturm-Liouville by saying P of x Liouville. I should just give up and just say it like it is. Sturm-Liouville slugger. And then W of x is equal to 1 over the square root of 1 minus x squared. Now, these are all just different situations in which Sturm-Liouville has appeared in mathematics, or in physics. And let's go look at the Wikipedia page to see if we can learn anything more about the nice subtleties that Sturm-Liouville is telling us. Let's see, this is important in applied mathematics, where Sturm-Liouville problems often, or occur very commonly, particularly when dealing with separable linear partial differential equations. For example, in quantum mechanics, the one-dimensional time-independent Schrodinger equation is a Sturm-Liouville problem. And so these are an entire class of solutions, or entire class of problems, each with their own solutions, and these solutions show up constantly in physics. It's certainly amongst the most used item. Like, they never teach you that this is all like one classification of differential equations when you're in like did anyone take, like me, did anyone take like the scientist or the physicist edition of differential equations? Because I took like a physicist brand of that, and it was very different than like what you would see in the mathematics one. Where are we at now? Okay, so we did that. I don't know. Did that tickle your fancy, NC? Did you like that? I did not realize when you had asked me to talk about that what the Sturm Sturm-Liouville was, and I had no indication that it covered literally everything covered by differential equations in physics. That's wild. Yeah, it's pretty wild. And so the context of PDE, you get a system of these equations that you can get into linear algebra. Then you get to the... Oh, I see what you're saying. But then wouldn't you still just be getting the... so you get a series of these PDEs, is what you're saying, based off the lambdas. And then you can get... would it be the lambdas or the y's? And then you can get to the linear algebra of it. So similar to like what we're talking about with like the dynamical matrix, right, of the force equations of like in condensed matter, where you can build wave equations after wave equations of the modes of vibration. So you build the modes of vibration, each of them is a different solution. But anyways, yeah, so that's Sturm-Liouville. It shows up everywhere, and then I guess what NC was saying is like you can get a series of equations similar to the modes of vibration that I was showing you in this string, and like basically what you would do is like, so for a string of atoms is where I'm going with this, NC. Like a string of atoms has, you can talk about where each atom is and the effect of the force on the entire string by writing down a matrix of all of the force equations for a given system. And what you can do is you can solve all of the... This is only for physicians? For physicists. No, it's for everybody. This is open to the public. This is not only for physicists. This is for anybody who would like to learn anything about physics. If you have a question about physics, ! Ask and then your question. And I'll happily try to answer it. I might not be able to. There's always that situation. But the idea would be like you have a string of atoms and you can figure, and they're connected with springs, we'll say, it's connected with springs. And basically the forces on each of the atoms is going to be like, it's going to be like a matrix element, a force on each of the individual atoms. And what you'll get is an entire matrix of these little force equations of each individual atom. And then the eigenvalue, and this is similar to a wave equation solution, right? You can actually set up an entire linear algebra like he's talking about, or an entire system of equations with a full set of eigenvalues and eigenvalues and eigenvectors and eigenfunctions, all completely solving the wave equation. And I guess there's a way to do this with using the Sturm-Liouville or Liouville form. That's pretty interesting. Nothing that I've seen though. Like NC, did you see this when you were an undergraduate? Because I never saw it as an undergraduate. Maybe I'm saying if y is a vector, you get a system of, and you get a tensor operation, if I recall, acting on the y vector. Sure, but wouldn't the y vector... okay, hold on. Oh, I see what you're saying. Yeah, maybe. I guess so. I guess you could. I never even thought about the tensor applications of it. Kind of like a space, like a vector space, as a solution to each, as a solution to these. Interesting, NC. That's pretty cool. I never thought about acting on it as a vector space, but I see what you're saying. Interesting. Very cool.